Hello everyone, welcome back to another virtual lesson in physics. In our last lesson, we looked at how we add vectors together and simply using the head-to-tail method, and we can also use the parallelogram method. Here is an example just of some vectors that point in a specific direction that you add together. So if they point in the same direction, the resultant of those vectors would just simply be the overall sum of them two as they are placed tail to head with one another. And if they go in opposite directions, then of course the resultant would be the balance between them two vectors. So as we say, the resultant is a single vector that shows the overall effect of all the other vectors acting together. So it always is drawn from the beginning, where the first vector starts, to the end, where the last vector ends. And so you can see that the resultant here is the difference between vector A and vector B. If you add more than two vectors together, you simply arrange them to each go head to tail with one another, and the resultant will start where the first vector starts and end where the last vector ends. If we have vectors that do not go collinearly, or they are not on the same plane or in the same straight line, then of course you have to start using trigonometry. And if the vectors go at 90 degrees to each other, like here, say a 5 and a 10 kilometer vector, a 10 kilometer vector due north, so it would point up, and a 5 kilometer vector due west would point to the left, and the resultant would start where the first vector starts, and it would end where the last vector ends. And that will be, of course, the hypotenuse of this right angle triangle that you can simply use by the Pythagorean equation, which in this case will be 5 square plus 10 square. That means necessarily, therefore, that the resultant will be the root of 125. And you can then go work it out from there. Here, the resultant again starts where the first vector starts and ends where the first vector ends. The trick now comes in for you to express the direction of these resultant vectors. And for that, you always need the angle theta between the tail of the resultant and the tail of the very first vector. That will give you the overall direction of that resultant vector, and you're going to use simple trigonometry to work that out. So in order to work out theta there, you know that a right angle triangle has, and with an angle there, it's got an opposite, adjacent, and hypotenuse side relative to that angle. And so if this is the opposite side, this is the adjacent, and this is the hypotenuse, we can now use what we have and express those two sides in terms of a trigonometric function of that angle. So we know that the tan of theta will be opposite over adjacent. And from there, you're going to work out the anti-tan of 5 over 10, which is a half. You work that out and you get your angle, please, in degrees. The same here, you're going to work out that angle using trigonometry. Opposite over adjacent will be the tan of theta. So the tan of theta will be 40 over 30. To get theta alone, you simply get the arctan of 40 over 30 and you work it out. And please give your answers to do decimal places. Never leave it in surd form or in fraction form. So there's some more examples you can work through, and we have explained the trigonometry. You had to do that exercise, which you have marked. We now move on to this concept of components of a vector. So components of a vector is really easy to explain if you start from the fundamentals of geometry and you go to the Cartesian plane and basically look at the concept of coordinates. So let me start you with some simple math revision. If you are given that point over there, and I say can you please give me the coordinates of that point within that Cartesian plane? This is your x-axis and this is your y-axis. Of course, this is your Cartesian plane, two-dimensional. Can you give the coordinates of that point? Well, we know that it will be 3, 4. Why? Because in any sort of coordinate form, we always write the x value first and then the y value second. The x value can be simply be found by going to the point and dropping down a line and see where it cuts the x-axis. That is your x value within that coordinate. Then also going back to that point and shooting across to the y-axis, and you will see that is your second value within that coordinate. And so we're saying, if I now have to go and work out, for example, what is the length of that line that I've just drawn, and it is quite jagged. Let us try and do a straight line. Okay, can you work out, let's call this length r, and we say, of course, can you work out the length of r? R, as you know, is simply if we complete a right angle triangle with the x distance as that horizontal line and the y distance to that point as the vertical line in that right angle triangle, then of course we can say r is going to have this length. Of course, we know it's going to be 5. Why? Because r is the hypotenuse of that right angle triangle, and it is 3 squared plus 4 squared, which is 25. And so that's r squared. So r is the root of 25, which is 5. But what we are trying to focus on at this stage are the horizontal and vertical components of that vector r. We call them, as I've said, components. So you can take any skew vector and break it up into its horizontal and vertical component. If I, for example, take a line here, and I say, that is my vector r, can we please break it into its vertical and horizontal components? Well, all you have to do is take the x distance to that point and then take the y distance from the origin to that point, and we say, well, this is going to be -8, and this distance down from the x-axis down to this point is -6. So the horizontal component of r is -8, and the vertical component of r is -6. This is how we do horizontal and vertical components.